Hello, year 11. Today we're going to do Newton's laws and inertial mass. Here's the work folder and here's the PowerPoint. Now, I want you to walk out of this lesson knowing the 3 laws of motion as a minimum. So if you can write those laws down and learn them, that is perfect, because there's a lot of stuff that pops up in this that is more difficult. Don't worry if it becomes a bit overwhelming. Just go back and make sure you know those 3 laws of motion, and then you are sorted. So let's get started. Let's recap resultant forces. Remember, a resultant force is where you add up all the forces that are working on an object and figure out kind of the total, like if it was to be one force, that total force. Well, if we look at the top one, this would be 500 to the right and 50 to the left. So overall, because they're opposite in direction, right? Overall, they would cancel each other out a little bit, but you'd be left with 450 newtons pointing to the right. So if you want to pause it and do these other 2, and then I'll go through them in a second. Right. Hopefully you've had a little think about them. Now, on this bike, we've got 150 newtons going to the right. We've got 50 to the left and 100 to the left. The forces on the left actually will add up to be 150, which is like exactly the forces to the right. So overall, you will have no resultant force, a 0 Newton force, so no resultant force at all. And we should remember, if there is no resultant force, this bike is either stationary or moving at a constant velocity. Well, look at the bottom one. You've got 250 newtons to the right, you've got 125 to the left, and you've got 175 to the left. If you were to add both of these on the left together, you would get 300. So let's create our resultant force. Well, 300 is bigger than 250, so our resultant force would be 50 newtons to the left. Now, why are these Newton's laws of motion? Well, it's because they were proposed by Sir Isaac Newton. He's a pretty cool dude. He pretty much changed the way we look at acceleration and forces, and we still use his equations now. They're very useful. He did some other stuff too, but we don't need to talk about that in this lesson. This is the first law. I'd like you to write this down. This is one of the 3 things that you need to learn after this, or through this lesson, after this lesson. First law, balanced forces mean no change in velocity. When I say velocity, I'm talking about there's no change in speed, and I'm talking about there is no change in direction. Okay? If the speed or the direction change, the forces are not balanced. Okay? So, remember, velocity is the speed in a certain direction, so as long as there is no changes in the forces on an object, it will either stay stationary or travel at a constant speed. Now, these are the same thing. If I have a speed of 0, which is not moving, and I continue to have a speed of 0, that is a constant speed. It's just 0. But people forget about that specific case, so we mention it. If your forces are balanced, you are either stationary or you are moving at a constant speed. So let's have a look at an example. Okay. If you've got tug of war, Team 1 and Team 2 both have 6 newtons of force. Maybe they've got 6 people that are identical on each side, and they're pulling, and they're at a stalemate. Okay? They can't move the rope to one side or the other. No one wins. The resultant force is 0 because both people are pulling with exactly the same force. Or you could say the forces are balanced. So there will be no change in velocity. If they were stationary before, they will be stationary now. Right. I want you to do maybe 2 of these. Okay? I just want you to get the idea of drawing some force diagrams, or free body diagrams. So I'm going to do a book at rest on a tabletop, so I'll do number 1. Here's my tabletop, right? Here's my book. The weight force is going down on the book, but there is an equal force going up called the reaction force. The table is pushing against the book. This book is stationary. Okay, the forces are balanced. This is an equilibrium. So I've done number 1. Let's do something. A lorry slowing down. I'll do number 6. So here's my lorry. There it is. Very nice. I'll give it some wheels. There's my lorry. The lorry is slowing down. So let's just say there is only 2 forces acting on this. Let's say there's a driving force. Let's say the guy's still got his foot on the accelerator. There's a driving force. So that is D for drive. There is a drag force or an air resistance. I'm going to call it A dot R for air resistance. Now notice the force for air resistance is a lot bigger than the force for drive. Okay, he might have took his foot a little bit off the accelerator. The drive force is a lot smaller, so the air resistance is slowing him down. The resultant force is that way, right? Because air resistance is much bigger, so this person would be slowing down. So pick 2 of these and draw the force diagram for them. Just this little bit of practice. If you want to, you can do all 9, but it's a lot of diagrams. You'll have plenty of practice throughout the whole course doing them. Now, Newton's second law. A resultant force means an acceleration. So I'd like you to write this down, please. Let's go back to our previous example. Right, a resultant force means an acceleration. Well, let's have a look. If before they were stood still, remember when it was 6 newtons and 6 newtons on both sides, they were stood still. Now, team 1 is starting to win. Team 1 has got 6 newtons, and team 2 has got 4 newtons. Okay, so the resultant force is in 2 newtons in that direction. So, let's just say team 1 is on the left. What happens is this rope here is going to start to move to the left because team 1 is winning. Now there is an equation that shows this, which we'll get to in a second. Now this next slide is about a required practical. We can't do this now, but I'm going to tell you that it exists. What you do is essentially you get an object, you hang a force from it and see how quickly it accelerates. So you'll have like a car on a table. It'll be attached to a string. You'll put a weight on the end and it'll pull the string and you'll see how quickly it moves. You'll then change the weight on that object and you'll change the mass of the object and you'll see what happens. Now, this is still the second law. A resultant force means an acceleration, but I need you to write down this equation. If you don't know what the symbols mean, write them down too. If you are asked about Newton's second law, you should just write F equals ma. That is Newton's second law, and that is the one that you'll be asked to use to do a lot of calculations. If you are given the mass and the acceleration of something, you can calculate the force that was exerted. And that's the same for if you are given 2 out of 3 of these variables, you can calculate the third one. So if you're given the force and you are given the mass, you can calculate how much something will accelerate. So please write down that equation. Now, from the equation, I'm going to write F equals ma. F equals ma. If you've got a bigger force, you will have a bigger acceleration, right? If you've got a bigger mass, it's going to be harder to accelerate something, right? If you go to, I don't know, your little brother and push him over, it's going to be easy. But if you try and do that to your dad, he's got a bigger mass, it's going to be much more difficult, right? There's an easy example. If you go outside and try and push the car down the road, it's more difficult. But if you try and kick a football, it's a lot easier. Now, if you've got a bigger mass here for this third point, and you want something to accelerate as fast as something that's small, you'll need to have a bigger force. So looking at the equation, you can kind of understand what's going on. But if you relate it to real life, think about heavier things, or I should say things that have got more mass, and they're harder to move, aren't they? You need more force to get them to move. And that kind of makes sense to me. Now, I've got a task here, and I'm going to take you through these. So as an example, let me just go on to... Let's cut this off like that. Let's see if I can get it to stick on here. Right. So second law. A car has a mass of... I've lost my pen. 1750 kilograms. Has an engine which provides a driving force of this. At 7 meters per second, the drag force is this. Find its acceleration when setting off from rest. Assume there is no friction. Right. First of all, I need F, M, and A. Okay. And I'm going to draw my diagram. Now, I know the mass of the car is this, 1750 kilograms. What this first thing is saying is when this car is setting off from rest, it has a driving force like this of 5,200 newtons. Its mass is that. So for part A, if I have a force of 5,200 newtons and a mass of 1750 kilograms, what's the acceleration? Well, let's use our equation. F equals ma. There's my diagram. When it says, when first setting off from rest, assume there is no friction at rest, and it says the car produces a driving force of this, that is my car's driving force right there. This is my car, by the way. That's my car. So, 5,200 newtons equals 1750 times by A. I'm going to get my calculator out. Now, hopefully, you are getting the hang of this from maths. I want A equals. I need to make A the subject, or I need to get A by itself, however you want to phrase it. So to get rid of this 1750 on the right-hand side, I am going to have to divide both sides by 1750. Okay? Right? If I do that, that and that cancel out, and I'm just left with equals A. Well, what's 5,200 divided by 1750? It's about 2.97. 2.97. Okay. So the acceleration, I'm just going to flip it around now, equals 2.97, and the unit is meters per second squared. Now, I appreciate I did that quickly. I'm just going to recap a little bit of what I just did. And get rid of that. And get rid of that. Right. We'll do it in pink. The question essentially said, I have got a force of this. I have got a mass of this. What is my acceleration? Ignoring all of the words that are in this question, right? All it has said is, if this is my force and this is my mass, what is my acceleration? Well, this is my equation that I am going to use. If I use this equation, my force was 5,200. My mass was 1750. So I was left with 5,200 equals 1750 times A. I needed A equals. So I rearranged it, just like you do in maths, and I got A equals 2.97. And the unit for acceleration is meters per second. Now, let's cut this in half and let's do part B. B says what's happening when it is at this speed. Now, if we look at the question, I know the mass of this object is 1,750 kilograms. That will not change unless I don't know, chop the wing mirrors off or something. It says the driving force from here, the driving force of my car is 5,200 newtons. But it says at this speed, the drag force is 5,100. So this is my drag force, 5,150 newtons. This is my drive, and this is my drag. Now, I like to draw diagrams because it helps me understand. What is the resultant force on this object? So let's redraw. We will do it in a bit of green. So now, what is the resultant force? Question mark. Well, let's draw my box again. The box is still 1750 kilograms. I'm actually going to change my pen to be a little bit thinner. Okay, that's a bit better. The box is still 1750 kilograms, but these two forces here are equal and opposite, so they kind of cancel each other out. But the drive force is 50 newtons bigger than the drag force. So actually, I've got an overall resultant force of 50 newtons acting in that direction. So let's do F, M, and A again. I'm going to go back to pink. I kind of like that colour. It showed up quite nicely. So my force is 50 newtons. My mass is still 1750. My acceleration is, I don't know. So let's get my equation again. F equals M times A. My force was 50 equals my mass was 1750 times by A. So I'm just going to show you. Remember, this is my force, and then we calculated it as 50. This is my mass. We just literally substituted the numbers in. Okay, we still don't know what A is, so we're just going to leave it as A. Right? Well, if I've got 50 equals 1750 times by A, I need A by itself. So again, I'm going to divide both sides by 1750. Now, changing colour. Let's go to blue. Right, so over here, that's too dark, we'll go green. I'm going to rewrite this, okay? So I'm rewriting this over here because I'm running out of space. So now I've got 50 divided by 1750, because remember this and this will cancel out, equals A. Now if I put that into my calculator, 50 divided by 1750 equals, so acceleration equals 0.029 meters per second squared. So these are probably the most difficult questions I'll ask you, right? They will just give you some words on a page, and you will have to then, one, draw your diagram, okay? After you've drawn your diagram, you will have to calculate any resultant forces that are there, okay, and then plug it into your equation. If you are able to draw the diagram, the free body diagrams like this thing is a free body diagram, or a force diagram, or this, right? These are your force diagrams. Then what I did is I converted it into a resultant force and then just used my equation. Remember this equation, this is Newton's second law, F equals ma. That equation, plug the numbers in. Even if you do not know how to rearrange, if you put the correct number in the correct place and just leave it, say for example, I'm going to take this one over here. If you had F equals ma and then you wrote 50 equals 1750 times A, that is a mark. Just leaving it like that, even if you do not know how to rearrange it. Okay, right, let's go to this. Let's go back on here. Now, let's talk about inertia. If you had 2 boxes of sweets, and you had, one was empty and one was full, how would you know without taking the lid off? Well, you would probably shake it, right? But let's say you couldn't hear what was inside. You'd probably be able to feel it's heavier. But let's say we're in space. You can't feel the weight of something. You're floating in space like an astronaut, right? What you could do is you could shake it or you could push it. One of them the one that's easier to push has more mass. This is called inertia, and it comes straight from, remember the equation F equals ma, right? If you want something to accelerate more and it's got a bigger mass, you've got to push it with a bigger force. And this is important because it works even if you're in space and there's no gravity. Now, so let's move on to our third law. This is the reaction forces. Now, Newton's third law is if you push something, it will push back with an equal and opposite force. So if you look here, if you push a pram, the pram will push back against you just as hard. When you stop pushing the pram stops pushing you. Next time you push something or pull something, you are pushing it and it moves, but the reason why you're feeling it on your hands is because it's pushing back against you. So that when you feel that you're pushing something, it is that thing pushing against you. So that is third law, that is the reaction. Okay? So I don't know if you ever watched Dancing on Ice or whatever it is. I don't really watch TV, but yeah, they always do things where they'll be skating and they'll push against each other and both of them will go off in the opposite direction. Okay? When they push against each other, they are pushing with an equal and opposite force. Because if skater A pushes skater B with a force that looks like this, then even if skater B does nothing, the force will always be equal and opposite. If it wasn't, you would end up pushing your hand through their hand, which wouldn't be very nice for them. Okay. So, third law basically says that every force is going to be in the same size and in opposite directions if you exert a force. Right? So they will accelerate away from each other in opposite directions. So Newton's third law. A force will be opposed. I'm just going to put will have an equal and opposite force. So write that as your third law. I'm trying to simplify it as much as possible. Okay, so let's think of another one. Maybe something that's a bit easier. I think it's easier to think about pushing against things that aren't living. So if you're a swimmer, if you push against the water, okay, you move the water away from you, right? But the water will also push against you, which moves you away from it. So if you push against the water pushes back with an equal and opposite force. So if the force is equal in size, but that direction is exactly opposite. Okay, so Newton's third law, a force will have an equal and opposite force. So I'm going to discard this, and we're going to quickly look at an exam question. That is not, it's here, there it is. Okay. So I want you to have a quick go at this exam question. They're quite straightforward, it won't take too long, but most of them are just putting arrows in boxes or like ticking boxes. It's mostly so you understand the concepts behind it. So pause this video, have a quick go of them, and then come back. So let's hopefully you've paused it. So it says, the diagrams A, B, and C show the horizontal forces acting on a moving car. Draw a line to link each diagram to the description of the car's motion. Draw only 3 lines. Right. A is the trickiest one, I think, because these forces are equal and opposite. So this car is moving with... So this car is in equilibrium, I should say. But this force here is drag or air resistance. Right? So if there is air resistance on a car, it has to be moving, so this car is not stationary. But because the forces are balanced, it's moving at a constant speed. B, you can see the forward force is greater than the force pulling backwards. So this has to be accelerating forwards. If you look at C, the forward force is smaller than the force pulling backwards. So this one is going to be slowing down. Right, part B. The front crumple zone of a car is tested at a road traffic laboratory. This is done by using a remote control device to drive the car into a strong barrier. Electronic sensors are attached to the dummy inside the car. I'm sure you've seen videos of this before. It looks pretty cool, where they crash a car into a wall and see what happens to the dummy and the car. So part 1, draw an arrow in box 1 to show the direction of the force that the car exerts on the barrier. So what direction does the force, this car here, which force, sorry, I'll start that again. The car is going to exert a force on this barrier, but which direction is that? Well, the car is pushing the barrier, isn't it? So the car has to push the barrier in that direction. It says, draw an arrow in box 2 to show the direction of the force that the barrier exerts on the car. Now, because we know that the force has to be equal and opposite, we know that the force must go this direction. It's in the opposite direction. But if you think about it, the car is pushing the barrier, so the barrier has to push back to the car. So the car is pushing the barrier because the force is always going to be opposed by an equal and opposite force. The barrier must be pushing to the left. Right. Part 3. Complete the following by drawing a ring around the correct line in the box. The car exerts a force of 5,000 newtons on the barrier. The barrier does not move. The force exerted by the barrier on the car will be equal to 5,000 newtons. Remember, if the barrier does not move, the forces must be equal and opposite. Remember Newton's second law. If there is no acceleration, okay, there has to be no resultant force. Okay, which one of the following gives the most likely reason for attaching electronic sensors to the dummy? Now the whole point is that it is to measure the forces exerted on the dummy during the impact. We're trying to see if cars are safe for people to be in if you get into an accident. Right, question 3. As you can see, I removed question 2 because I didn't want to do it. So if you look at the mark scheme, there will be question 2 in there. If you're trying to mark your answers without this help, just ignore question 2. Right, when two objects interact, they exert forces on each other. What statement about the forces is correct? The forces are equal in size and act in opposite directions. Remember, this is Newton's third law. Part B. A fisherman pulls a boat towards land. The forces acting on the boat are shown in diagram 1. The fisherman exerts a force of 300 newtons on the boat, and the sea exerts a resistive force of 250 newtons on the boat. Describe the motion of the boat. Well, you know that the resultant force is going to be 50 newtons in that direction. So, because there is a resultant force, there must be an acceleration. So this boat is accelerating. Okay, for 1 mark. And which direction is it accelerating? To the right. There you go. The boat is accelerating to the right for 2 marks. When the boat reaches the land, the resistive forces increases to 300. The fisherman continues to exert a force of 300. So let's draw the diagram. This time I will treat you to not drawing a box, and I'll try and draw a boat. So the fisherman's got 300 like this, and the ground is resisting with 300 like that. That's an N. Before, remember, the boat was moving. Before this situation, the boat was moving. Now the forces are balanced. That means there is no acceleration. But because the boat was moving before, it will continue to move now. There will be a constant velocity to the right. Okay. Explain your answer. There is no resultant force. Okay, so for 2 marks, the boat will continue to move with a constant velocity to the right. They might want you to say the forces are balanced. So the boat continues to move with a constant velocity. Scroll down. And that's it. There you go. Hopefully those questions help you understand a little bit more. But once you've done them, please email them to me. And I'll see you tomorrow.